main problem that we have at the moment is that we need to have high Reynolds number, data which have simultaneously high Reynolds number, resolution of all the scales, and well-converged statistics. You have seen this morning with Beverly that you can have very high Reynolds number with atmospheric experiments. You can have very good resolution of the small scales because the small scales are too small, but the statistics is a major problem. So to get high Reynolds number, if you just take the definition of the Reynolds number, you have different ways to get high Reynolds number. You can increase the velocity, then you limit it with compressibility effects. You can increase the size. You can increase the density with pressurized experiments, for example. And you can also decrease the viscosity of the fluid, for example, with high-energy experiments. So, just to illustrate that, I'm going to show a few experiments which have been done in this, with different options. One which is very well known is this circular pipe experiment in Princeton. Basically, it consists of a small pipe with a diameter of 30 centimeters, so it's very small. But it's into a plenum, a chamber basically that they can bring to 200 bars. So the higher basically the density of the fluid, and you manage to get extremely high Reynolds number up to something like 38 millions. The main drawback with that is that the small scales are very small and very difficult to resolve. Another option is this cryogenic experiments. There is an example at CERN where they use liquid helium, and basically with this they reduce the temperature. They have very low temperature, so they have low viscosity and high Reynolds number. Here also they have extremely high Reynolds number, but the same problem is that the viscous scales are very small. Now, another option, this is what we are developing with Alessandro in Bologna, is to increase the size. And here we're developing a long pipe with 1 meter diameter. It's 120 meters long, so it's very big. And you can go to a moderate Reynolds number, which are still very interesting in terms of thermal research. But the viscous length scale remains fairly big, and you can basically resolve that with standard hot wires, for example, or probes basically of decent size. Now, well, okay, this is now the other options. We have seen this morning is this other experiments. So basically, we have very as Beverly described in detail this experiment. Now, so this is just basically to introduce the need of this high Reynolds number experiments and the way that you have that you can get it. I'm going to talk about a few issues with experiments, and this can be interesting, I guess, for the people making experiments and also for the one working with numerical data to understand also what are the constraints that we have with experiments and basically how to design experiments. Now, the main things with internal facilities is the flow quality. Now, the flow quality is defined by a number of parameters: flow homogeneity, angularity, turbulence intensity, noise level, temperature and velocity stability, and pressure gradient control. So all these quantities have to be monitored and documented to be sure of what you're doing with your experiments. Now there are two main types of internals, the closed loop and open loop internals. You probably know all of them. You will see the MTL, which is a closed loop internal later on. So basically, test action can work with ambient pressure. You can reach very high flow quality. You can control the flow very accurately. Now the problem is that basically you're recycling the same air again and again. So as you're injecting energy into it, you have to cool it down if you want to keep the temperature constant. The other option is the open loop internal. They are simpler and cheaper than the closed loop. control the flow conditions. And as you draw in air from the outside, you're drawing air from different temperatures, and also everything which is in the air. So you can have a filter, but you will always have some particle going into it. Now, dust contamination is problematic with wires we have seen before, because wires are very small, so if you have dust particles hitting the wire, you can damage the probes, and you can also reduce the lifetime of these probes. It's also important with different temperature measurement techniques that we can going to see later. Now, open loop, they need more power, and depending on the setting, you can have test action with ambient or slightly lower pressure, depending on the position of the fan, if it's upstream or downstream. So now, once you have wind tunnel, basically there are two main types of flows if you want to go for canonical flow that you can have. Either you have a flat plate inside a test section, so a plate mounted at mid-height, or you have a flow developing on the wall. Now, the flat plate, which is in test section, the advantage is basically you have a clean flow incoming onto the flat plate. It's easier to condition the surface because basically you can put inside, take out elements, so you can modify it fairly easily. The temperature of the surface is normally the same as the flow because it gets into equilibrium. Now the problem is that when basically you have flat plate which sits in the wind tunnel, if you have traversing mechanism, for example, to traverse the sensors, you have bulky elements which are just underneath the flat plate, and they generate blockage around the flat plate. Now, if you have flow developing on the wall, for example, like this one, it's just like a duct when you have open hand simulations. You have very easy access through the wall because basically the wall is directly your flat plate, so you can easily have all bulky elements mounted outside. And you also use basically the full height of your channel. So it's different advantages. Now you have to be a bit more careful about how you condition with the upstream conditions. So first thing, of course, for control you need to have a system that controls your temperature, your velocity, and you have good reference velocity and temperature measurements if you want to be able to compare accurately what you're doing with other experiments. Turbulence manipulators, this is basically our inflow conditions, and here you can do a lot of things. We normally use, these are the different elements that are normally used basically to condition the flow before the contraction. You have perforated plates, two-dimensionalized large velocity differences, honeycombs, and screens, different type of screens that reduce the amount of turbulence in the flow and homogenize the flow. Now once you have that, you have the contraction. So the contraction is basically when you reduce the size of your section to the size of the test section. We normally have a contraction because the return part of the wind tunnel is at low velocity to have low losses into the circuit. Of course, when you have air traveling at high velocity, it generates a lot of losses. So normally you increase the size of the return part to decrease the velocity, and then increase the losses. Then also with the contraction you increase the flow quality. So these are these two effects. Now the maximum contraction ratio, which is bringing something positive into the flow quality, is 9 to 1. Doesn't really serve to go at a higher contraction ratio. Now the main goal of the contraction is to generate a flat velocity profile in the inlet, and to avoid, so you want to avoid to have separation compression into the contraction in order to have a low intensity level. So this is the next thing is basically you have your flat plate, you have your boundary layer developing on it. Now, as you know, you have first laminar boundary layer, then you have transition and a turbulent boundary layer. As you have seen yesterday with Henrik, the turbulent spots, if you have no control of them, they appear randomly in space. And in order to have well-defined conditions for turbulent flows, we normally fix the transition. So fixing the transition means we put devices, this is roughness elements, we have three different configurations here, and basically going to trick the boundary layer to make it perfect. So the transition will fix the virtual origin of your turbulent boundary layer. Now, it is also important to fix it in the spine-wise direction, because as you have seen yesterday with this, the video from Henrik, these turbulent spots appear at different places. So you never know exactly where is your, where's your turbulent boundary layer starting to develop. So in order to have clean flow condition, you fix this with this kind of roughness elements. Now the other thing also is that when you change the velocity in your ultra, you will change the thickness of the boundary layer. So the behavior of the boundary layer regarding the tripping is going to change. So when you design your experiment, you have to make sure that the tripping is robust enough that you have a fairly fixed transition. Now this is graph. This is this three configuration. This is from Ramis, and you see here that H is the shape factor, so it's the ratio between the spacement thickness and the length thickness. And now, basically, you should have. This is also one thing that you should always do with experiments. Is that when you start an experiment, you should make an analysis of the conditions to be sure that you're not measuring just the behavior of your conditions, but really the behavior of the flow. So it's a sensitivity analysis that you should actually perform with most of your parameters to be sure that this is consistent with the flow, so that basically you're not measuring just the effect of something which is not related directly to the flow. So, for example, here, if we you see that these are the green and the black. The green and the black are these two ones, and the red is this one. Here, basically, the behavior starts to be different. So, obviously, you're forcing too much the boundary layer, and so we're introducing some configuration that actually transform the flow. So this is also probably we were discussing this with Philip yesterday. With DNS simulation of boundary layers, when you have basically inflow conditions, this is also probably something which is actually very important that you have to investigate in order to be sure that what you're measuring, simulating is not related to the inflow condition, but really to the physics of your problem. Now, this you don't have it actually in the slide, but the printed version. This is an example. This is a study made by Tohan. It's many shear factors measured for many different experiments, and you see that basically they all, most of them fall on a line, and then there are some outsiders. And this suggests that basically if you do your experiments correctly, if you have the right tripping and so on, you should get very similar data. Now, the pressure gradient control is also something which is important when you have a test section. Basically, the boundary layer is going to be blocked. So when you have boundary layer experiments, so not something like a back or a pipe flow where the flow is really blocked. The flow is evolving with the streamwise coordinates, so you have this displacement thickness, the boundary thickness increase, so we have displacement thickness, which increases also. And if you have a fixed configuration, you will have an increase of the mean flow velocity. Now, to avoid that, what you normally do is that you diverge the roof slightly so that you decrease the velocity and keep the free stream velocity constant. So you have a zero pressure gradient. Now, this is an example of an experiment. This is in India. This was done by Österlund in 1999. This is a traverse of the mean velocity in the longitudinal direction, and as you can see, the velocity deviates by about tenths of a percent. So this is basically what you can achieve when you have well-designed experiments in terms of velocity or zero pressure gradient. Now you can measure that either with pressure cups, or you can as a wall, or you can also basically traverse with a hot wire mounted on the test section. Just to illustrate what is the effect of this pressure gradient, this was a test performed in Chicago, in India. The pressure gradient of 4% result in friction velocity, in the change in the friction velocity of about 4%. Now, it doesn't mean that this is there is a one-to-one relationship. Basically, this is just to illustrate that a pressure gradient of 4% is not very big, but it has a very large effect on the wall shear stress. So it's very important to control very accurately these two velocities. Now the blockage, as I said before, if you have a flat plate mounted into your section that you have bulky elements underneath, you will have blockage. Now blockage is basically the air has more trouble to go underneath where there are these obstacles that above it when there is no obstacles. Now to control that, you normally add a flap in the end. So you have the proton in this direction, you have your flat plate and that. If you have a big obstacle here, you can actually go like that, like this. And in order to prevent that, basically, well, what happens here actually is that you will have the stagnation point, which is going to come from below the streamline. So you will have a separation bubble here. You can. And this will basically disturb the lower boundary layer. So what you do is that you add a flap in the back, and you bring this stagnation point to the front, or even slightly above. Now, moving the flap when you have an experiment is not very easy, so what you normally do is that you go on the safe side, you put it high enough, so that you have the stagnation point slightly above, and that it is basically working for all four conditions. Now, downstream of the test section, only you have a diffuser, and there are two types of diffusers. You have long diffusers, and you can have there are different types, but two main types which are used for these applications: split diffusers and long diffusers. Long diffusers, which is basically, as you are going to see here in the MTL, they are fairly prone to large scale separation. So when you have a flap like that, the flap is going to introduce also some perturbation here in the back. And when you have the perturbation going into a diffuser, you can generate large scale separation. So what you do to avoid that, you may have to put turbulence generators on the wall of the upstream of the diffuser to re-energize the boundary layer and avoid separation. Now the alternative is to use split diffusers. So basically it's the same thing as your diffuser. I mean, if you have the diffuser on the side like that. Now what you're going to do is you put plates into it. So if you look from upstream, you're going to have something like a grid like that. So you divide your big diffuser into smaller ones. Now, with this, basically, you have the diffuser is going to be more compact, and you can basically the angles of the opening angle is going to be smaller. So it's going to be less sensitive for the same dimensions to separation. Now, the drawback, of course, is that they generate a little more pressure drop, but they are less sensitive to the input conditions. So, now noise level, this is also an important parameter. For noise, there are too many types of noise. There is the noise of the fan, this is the one we really want to avoid, and the noise which is generated by the flow. Now, if you want to perform measurement of the fluctuating pressure, you need basically to have an acoustic level which is low enough not to perturbate too much your measurements. And also, like in the MTL, if you want to perform stability measurements, you need to have very low acoustic level in order not to force instability modes acoustically. The requirements that was set for the MTL is 0.15 to the minus 3 times the pressure, the dynamic pressure. These are measurements made by Tsui of the pressure fluctuation, so it's the PRMS divided by the dynamic pressure, 2 times the dynamic pressure. If you look here, what is the smallest level of pressure fluctuations into the flow, this corresponds, this requirements corresponds to an order of magnitude lower than that. So basically you want to have an acoustic level which is an order of magnitude lower than that. And this gives, for example, in the MTL, 84 decibels, which is very low. Now this is at 60 meters per second. This is achievable only if you have mufflers mounted in the wind tunnel, so basically that you have acoustic elements that are going to suppress these, the noise from the fan. Typically, the noise from the fan at high velocity can go higher than, much higher than 100 decibels, so 120 or even 130. So to illustrate these different things, I'm just going to show quickly a few wind tunnels that are used for turbulence research. So this is the MTL that you're going to see afterwards. You have the fan. The section is here. You have a long diffuser of the fan, a heat exchanger. The heat exchanger is normally located in the region of the return circuit, which has the highest dimensions, because they generate a lot of pressure drop. So you want to have them where they actually the velocity is the lowest, so that the pressure drop are also the lowest. Here you have these turbines manipulators and the contraction. And you have test section, and here, for example, this longer diffuser. As you can see, also one thing with contraction, the slope at the beginning of the contraction is very gentle, and the curvature, sorry, and it's more severe at the end. Just saying one word about that, because we keep on seeing actually experiments which are with better designed contraction. There is often the idea that you can actually curve here as much as you want, have very high curvature at the beginning, and virtually positive concave curvature destabilize your flow. So you often, you can get, as you have also a laminar boundary layer here, you can get separation in these regions, and when you have it, you don't recover good flow quality. It's very difficult. Now, another example, this is the NDF at Chicago. This, to say one thing here, we can see that the turbulence intensity is extremely low. It's something like 0.03%, and the mean flow uniformity is also very high. Now, this is another example in Chicago, fairly similar design. The only thing that changes is here is it uses this as you can see, the flow uniformity and the turbulence intensity are very similar. I mean, these are two of the very good internals for this for turbulence measurement. Now, another one which is used a lot is this one in Melbourne. This funny name stands for high Reynolds number boundary layer internal. This is another type. Here it's a duct flow, so there is no. Sorry, I forgot to say that the two form ones have a flat plate mounted middle height. This one, on the other hand, has the flow developing directly on the wall. Now, just to make some publicity for what we're developing, in Bologna, this is this long pipe which is going to be interesting for high Reynolds number experiments. Basically, it's a very long pipe, it's 1 meter diameter, and its base, basically, the design is based on the different windows that you have seen before. So we expect also to have very high flow quality. One of the big advantages with this one is that it's a fully, I mean, it's different in the sense that this is a fully developed flow. It's not a boundary layer. So we can measure the skin friction directly, washes directly from the pressure drop. Now, this you can look at this the performance if you're interested. I'm going to talk now briefly because we have to close soon. Wash stress measurements. Now, there are mainly wash stress measurements. There are mainly two main type of techniques. There are direct techniques, where basically you make your service on the velocity profile, and you don't have to calibrate with any other the technique with any other shear stress calibration. The main techniques which are fall into this category is pressure drop, which is basically what you can do with pipe flow experiments, for example. Momentum techniques, wall balances, and oil fill interferential. I'm going to talk a bit more about these afterwards. And in the other category, you have these techniques. Basically, here you're going to hypothesize that you have a known velocity profile, that you know at least something about your velocity profile. So mainly, they are very often based on this logo that you have seen a few times here. These are basically you hypothesize that you have this log region here, and then you calibrate, you extract, for example, u tau here from your velocity profile. Now the problem here is that in order to know u tau, you have kappa, and we're going to see this afterwards. Now, so there are many different techniques, present tubes, closed plots. There are profile that use also this part of the chart of the profile, and the other part of the profile. I'm not going to talk too much about this one because they make assumptions that we don't want to make, because you don't know a priori if they are right or not. Now, there is a subcategory of these ones, of these measurement techniques, which are the near-wall measurements, the techniques that use basically the near-wall region. I mean, this is fairly robust, and basically this is hypothesizing that we have this linear region near the wall, basically that you have a correspondence between y plus and u plus. Now, this is supposed to be valid in up to about 5 wall units. If you look here, y, this line is u plus equal to y plus, so this is in log coordinates. You see that you have here, actually, this is DNS data from Philip Schlatter here, and you see that they start to diverge at about, this is, if you look in details, it's about here, which is about 3 to 4. And so, I mean, below 5 or below, sorry, back about 3, this region, this assumption is fairly solid. There is a lot of evidence of it. Now the problem is that this viscous surveyor is very thin, and when you increase the Reynolds number, you decrease the viscous units, so it becomes very difficult to access this region to make measurements. Now the people making measurements with different optical techniques, micro-LD, micro-PRD, for example, with hot wire you have other problems. Now I'm going to talk a little bit about mid-wall shear stress measurements. So wall shear stress measurements are crucial for all the scaling basically in a variable, because as we have seen, this is the velocity and the units which are required for most turbulent problems. Now there was this discussion about kappa this morning, the Von Karman constant. The question of it is, it doesn't seem actually to be very constant. People have been using, you have seen that there is a lot of variability in the values which are used. It goes from 3.8 to about 4.2 or 4.1. Now this is a graph which is taken from an article from Naguib and Cohen. This is this kappa constant for different flows, pipes, channel, and band layers. Now for pipes, it looks like it is fairly close to 0.4. Now if you look at band layers, it seems to be slightly lower. Now there's still a lot of debates about that. So this is the reason why we don't want to use any profile-based technique, as you have to hypothesize that the kappa has a given value. Now it seems difficult to know it a priori, and so direct techniques is basically the only solution that we can use, as long as we can understand much better what is the meaning and behavior of the kappa. We have been talking with some people about wall shear stress variability. Some measurements show that there are quite large span-wise variations. Actually, it seems to be more related to the setup of the experiments, and this is probably also related to the stripping problems that I was showing before. This is again measurements that were made in the MTL by Westerlund. Now, this is using Presto tube. In this case, it's not a big problem because you're comparing the same flow, same position. So even if these values are not exact, you have a fairly good information about the variability of your measurements. Now, basically, what you show is that the span-wise variability is about a fraction. This is 0.5%, so this would be something like 0.1, 0.2%. So you can get very high, very homogeneous span-wise wall shear stress distribution if you have a well-defined, well-designed experiments. Now, one of the technique which has been suggested, that can be used as direct techniques, is this based on this Karman momentum integral equation. Now, it turns out that the quantities that you have to measure are very difficult to measure, and in practice you have a fairly low accuracy, so this is not used very much. Wall balances, basically you have a floating element mounted on the wall, and you're going to measure the force acting on it. On one side, on one hand, basically you want to have very large elements to have the maximum size, the maximum force, and on the other hand, you want to have it small as possible to have to measure a local quantity, especially if you have pressure gradient. Now, these balances have been used or are used. For example, we have seen this morning in the presentation of Beverly for other measurements. Now, they are less and less used in wind tunnels. And a new alternative which is still being developed is a MEMS balance. So you see here, this is a small floating element which is held by this element. This is done with this MEMS. And what seems to be interesting is that there are a lot of errors which are related to these sensors, because first you have problem with the alignment here, you have flow that can go around the element, you have pressure gradients, you have all kind of perturbations that make this measurements difficult. Now, when you go to microsizes, it seems that these errors scale favorably and that it become interesting. Now, as far as I know, they are not commercially available, but there are still people working on that. Now, the pressure drop, this is the simplest method that you can use if you have a fully legal flow. So by fully legal flow, one intended flow which is not changing anymore with streamwise coordinate. So, for example, in pipe, this appears about 40 diameters for the mean quantities, even higher for the higher moments. Now you just make basically the balance between the friction and the pressure drop, and you can directly measure the skin friction. Now this is only applicable for fluid flow, so it's not an answer for ventilators, for example. Flow channels, you have to be careful when you apply it, and when you do it, you have to be careful about how you perform your pressure measurements. Now I'm going to finish by talking a little bit about oil film interferometry, which is a technique which is used a lot these days. So the principle is very simple. You put an oil drop on the surface, and the flow is going to blow it away. And you have a thin film of oil which is going to be on the surface. Now, in order to measure the thickness of this film, you use a light source. So you use a monochromatic light source and a camera, and you measure the interferometry patterns that develops on the surface of this film. As you see here, these are 3 different times, so you have this fringe is developing with time. And you can develop this equation where basically you relate the thickness or the thinning rate, the velocity, actually this is the velocity of the fringes directly to the wall shear stress. So this is one of the methods which is one of the direct technique which is actually very accurate and work quite well. Now the setup is fairly simple and inexpensive, but there are a few things that you have to be careful when you using it. So just going to talk about the procedure. First things that you need to have is a very accurate calibration of water viscosity. As you have seen here, the oil, the viscosity of the oil entered directly into the equations for the determination of the wall shear stress. So you have basically to know it with the accuracy which is good enough for these measurements. Then you have to make a special calibration with the target. This is very straightforward. Apply the image and then you analyze the images. Oil viscosity is measurement. This is one of the tricky business with this technique. What we use for that is a thermoregulated valve, like that. We put inside a capillary tube, and you measure the passing time of a sample of oil through this tube. Now, knowing the passing time, you can evaluate the viscosity. You measure the time either with an optical barrier or with a stopwatch, and what you need to have is a very accurate measurement of the temperature as well. Now, the accuracy of that is about 0.3%. This is what you can get with this calibration system. You see here, these are different experiments, different calibration that we perform in different places, different time, and the lines here are plus minus 0.2%. So this is fairly robust. Another thing is that the influence of the temperature variation and the viscosity of the oil is quite big. For one, it's about 2% per degree. So for 1 degree change in temperature, you have about 2% errors. So So if you want to go to higher accuracy than that, basically you need to have a very good measurement of the temperature. Now, if you just do a thermal analysis, you will see that the difference in temperature between the oil and the air and the difference of temperature across the film has a ratio of 1,000. This is basically the temperature you want to measure is the whole temperature. So the temperature of your oil film is going to be the one of the temperature. So you need to measure this temperature very accurately. Now there are different ways to measure it. I'm not going to talk too much about it. If some people are interested, we can talk about it. But basically you would like to have measurements with a fraction of a degree in the order of 0.2 degrees or something. Now once you have performed the measurements, then you have to analyze these fringe patterns. So here you have, for example, so there are different techniques that are used. I'm just going to present a few of them. This is here one of these fringe patterns. Now you can stack for each images, you can stack them sidewise, so you have the x coordinate here and the time coordinate, and then you fit these lines on the fringes, and the slope of these lines is directly the velocity of the fringes. This is called the XT method. Now the techniques that we have been using are technique based directly on the wavelengths, fitting a sine function on top of this is the intensity of the signal. So if you have these two techniques, if you have the fringes going in this direction, this is the intensity of the signal, and basically you fit directly function on it. What you can also do is just look at the location of the maximums and calculate the mean distance. Now, these all these techniques provide very similar results as long as you apply them carefully. Basically, normally, we have in our experiences that if you select the right region of the domain, there is no problem. They give very good results. Now, the one thing, I just go back here. Okay. Now, the question then is basically, in terms of time and in terms of span-wise, in terms of which region you have to use. In our experience, if you use basically at the beginning of the development of the film, you have a transient apparent decrease of the wall shear stress, because when you start by basically the oil drop is still developing, so you still don't have a real film. You're still measuring the development of your object. So basically, the first you have to be very careful with the first part of your data and just realize that you don't have this trend. But you see it clearly from with some of these techniques. Now the other thing is that on the side of the oil drop, you can have surface tension effect, and if you have surface tension effect, basically it can affect also the development of the film, so you should be away from this region. I think that we are getting at the end of the time. Yeah. So, looking at wall shear stress, I'm going to leave it out for now.